Okay, so today I'm going to talk about a joint work with Laura Forastiere and Alessandra Mattei. And the work is about selecting subpopulations of units for assessing causal effects in regression discontinuity studies. And sorry, Tom or someone else, if you can help me with the time, maybe give me a 10-minute or so notice. Okay, so, but of course, I'm happy to take questions in between. So as probably most of you already know, regression discontinuity designs are quasi-experimental designs where the treatment status changes discontinuously according to some underlying variable, usually known as or named the forcing variable or the running variable, crossing a pre-specified cutoff or threshold. Examples of such designs abound in the applied literature in many fields. For example, in education, oftentimes treatments such as scholarships or training courses are assigned based on a qualifying score or test falls above a pre-specified threshold. The same is true in, for example, medicine or public health, where prescriptions or therapies or drug prescriptions are assigned often based on again, a biomarker crossing a cutoff point. For example, statins are assigned depending on the cholesterol level, or a diet is suggested based on the value of the body mass index. Intuitively and let's say heuristically, the basic idea and identification, let's say, strategy in such designs is based on the, again, on the intuitive idea that units with values that are of the forcing variables very close to the cutoff point receiving different levels of the treatment are essentially almost as good as randomly assigned. This was essentially the intuition in the original paper by Tistel, White, and Campbell that introduced the design in the 60s. And of course, since then, the literature has on RDDs has evolved, and more recently, let's say over the last 20 years, it's essentially these kind of methods were reanalyzed and reintroduced, especially in the social and economic sciences, and for example, this year Nobel laureates in economic sciences, namely Josh Engrist and Guido Imbens, have contributed also to the methodological literature around RDDs. So the motivating example that I will be using also to show the benefits, let's say, hopefully I'm going to be able to show you the benefits of our proposal that I'm going to be using today is the evaluation of a social welfare program of the Brazilian government, which is called Bolsa Família, a program that started in 2003 and is still ongoing. the objectives of this program is or are the reduction of short-term poverty, and also, long-term poverty through conditional cash transfers. The specific causal question that I'm gonna address today is assessing the causal effect of this program on a specific health outcome, namely leprosy, which is again related also to poverty, or to let's say the difficulties of going out of poverty. It's a very bad disease. And in fact, we chose and used that as a motivating example, just because the Bolsa Familia benefit allocation rule is an example of an RDD. And in fact, in order to for a family to get a let's say this Bolsa Familia benefit, it must meet some eligibility criteria and also apply to get these benefits. For the application and the empirical analysis today, we will be using data on families who applied for some welfare program and are registered in this let's say administrative archive that is called Cadastro Unico in the years 2007-2008 for the first time. So eligibility, again, as I was saying, follows an RDD in that a family is eligible to receive the BF benefit if the per capita household income, which is our forcing variable, falls below a prefixed threshold, which is around 37 US dollars per month. Okay? So 120 Brazilian real. Okay, so and in fact, just because so eligibility follows what is known as a sharp regression discontinuity design, but the receipt of the benefit, in fact, would follow a so-called fuzzy regression discontinuity design, in that not all units, not all families that are eligible actually receive a benefit. And at the same time, for reasons that are not very clear, but at least we are still working with Brazilians to actually understand that, but some of the ineligible families do receive some benefits. So because our contribution is mainly focused on the selection of the subpopulation to conduct causal inference in RDDs, we here focus only on intention to treat effects, namely the effect of being eligible versus not being eligible, which may still be an interesting causal quantities, especially for policy purposes. For example, if you want to assess whether the threshold is 120 Brazilian real is in fact appropriate or not. So we will, again, just to make things clear, we will focus on the effect of being eligible to access these benefits, and therefore we are not going to assess the effect of the benefit receipt, but only the intention to treat effect of being eligible to receive these benefits. Okay. So as you, again, as maybe some of you are aware of, there are two main approaches to the analysis of these regression discontinuity designs. The traditional approach that has been developed mainly in the econometric literature views these designs as non-probabilistic assignment mechanism. So the forcing variable, the per capita income that I showed you before, is viewed as a pre-treatment covariate, possibly observed with errors, as in a recent paper by Eccles and et al. In published last year. And because the forcing variable is viewed as a pre-treatment covariate, an RDD is a non-probabilistic assignment mechanism just because, depending on the value of this covariate, the probability of being assigned treatment is either 0 or 1, at least in a sharp RDD. And so identification assumptions are usually smoothness or continuity type assumptions for the relationship between the potential outcomes and the forcing variable. And focus is on causal effect at the threshold for an infinite population. So asymptotic results are, let's say, used to assess the properties of the estimators of this causal effect at the threshold. So only for, let's say, units with the value of the forcing variable, namely family with the value of per capita income in our example, exactly equal to 120 Brazilian real. And essentially, given these continuity or smoothness assumption, a jump at the threshold of the some features of the distribution of the potential outcomes is interpreted under these assumptions as a causal effect. And essentially, the bandwidth, namely the units that are used to, let's say, estimate this quantity is chosen in order to minimize the mean square error or the asymptotic, let's say, expression of the mean square error of estimators. And these estimators are usually the difference of local regressions extrapolated to the cutoff point. Okay, this is the essence, let's say, of these traditional econometric smoothness or continuity-based approaches to the analysis of RD designs. In this work, and also in other papers that we wrote before, we instead introduced a slightly different approach that it's, in our view, a lot closer to the initial idea of Tister, White, and Campbell, this intuition that units around the cutoff point, not just at the cutoff point, but in a neighborhood of the threshold, are almost as good as randomized. So in a paper in 2015, we formalized a set of sufficient assumptions that allow to interpret RDDs as local randomized experiment. And again, this allows to, by viewing the forcing variable as a random variable whose realized value we observe, this viewing of the forcing variable as a random variable allows to formulate a probabilistic version of the assignment mechanism, and therefore also use, let's say, or formulate both estimands and estimation procedure within the framework, the potential outcome framework to causal inference. As I will try and detail in the next slides, on top of viewing the forcing variable as a random variable, the crucial identifying assumption is a local randomization assumption. Namely, we assume that at least a subpopulation of units exist around the threshold of the forcing variable, where, again, the forcing variable can be seen as randomly assigned. And because the eligibility or treatment is a deterministic function of the forcing variable, also the treatment status is randomly assigned for units belonging to this subpopulation. And again, the features of this approach is that first of all, we focus on causal effects for all the units in these subpopulation, and not just the subpopulation of units, which is a subpopulation of measure 0, essentially, of units with the value of the forcing variable exactly equal to S0. And these local randomization assumption also offers a way of selecting this subpopulation. Namely, we essentially aim at identifying units for whom the local randomization assumption is plausible. Okay, so it's a different, let's say, approach to the identifying the bandwidth, or again the subpopulation of units that we use to estimate causal effects. So essentially, the identifying assumptions are slightly different. The causal estimates are slightly different, just because they refer to a proper, let's say, observed subpopulation of units. The only problem, and this is what the work today is also about, is the choice of these subpopulation of units. So to make instead, or state these other assumptions that characterize RDDs as local randomized experiments, I will now introduce some notation that it's rather straightforward. So we assume that we observe a vector of covariates for each family. Z will denote the benefit eligibility status, 1 for being eligible, 0 for being ineligible. S and SI is the per capita household income, is the forcing variable. And Z, again, because we are in a sharp regression discontinuity design, it's a deterministic function or step function of these forcing variable. Potential outcomes. So sorry, the outcome of interest is a binary variable that takes on value 1 if in the family, in the ith family, there is at least a leprosy case for a given level of the forcing variable. Again, the set of sufficient assumptions that allow us to identify and then estimate the causal effect in these designs is, first of all, what we call a local overlap assumption. So we assume that there exists at least a subset of units that have a non-negligible probability of having a value of the forcing variable on either side of the threshold. So in principle, very rich family do not belong to these subpopulation. At the same time, extremely poor family also have a probability of always being eligible, namely always lying on one side of the threshold, right? So this is the local version of the overlap, the usual overlap or probabilistic assignment mechanism that it's that is known in observational settings. We also state the SUTVA, the stable unit treatment value assumptions, also locally. Namely, we assume that there is no interference, so the value of eligibility of other families is not affecting the potential outcomes of any other family. And also that for the subpopulation of units that is defined in the first assumption, we index their potential outcomes only with the eligibility status. So for different values of the forcing for different values of the forcing variable leading to the same value of Z, the potential outcomes are stable in that they only depend on the value of Z, not of S. Again, this is a local version of SUTVA in that it does not apply for all the units in the population, but only for the units belonging to the subpopulation defined by the local overlap assumption. Okay. Okay, so based on these two assumptions, only two potential outcomes are postulated to exist for a given family, and we are interested in these causal estimates. So our causal estimate is a local relative risk for the probability of having at least a leprosy case in the family, and for units belonging to this subpopulation. Again, as I was briefly saying before, the crucial identifying assumption is this local version of randomization. In that, again, for the units belonging to this subpopulation, we assume that the distribution of the forcing variable is free of the potential outcomes. And again, there are in the literature different versions of these local randomization assumptions have been proposed. Assumption 3 is the essentially is like assuming that a Bernoulli trial or complete randomization happened around the cutoff point for these subpopulation of units, whereas this other version that it's essentially a local version of unconfoundedness assumes that the distribution of the forcing variable is free of the potential outcomes only given covariates X. And so again, it amounts to assuming that for units belonging to this subpopulation, a Bernoulli trial took place with assignment probabilities that depends on the covariates. Okay. What are the potential advantages of this approach to RDDs? So what are the advantages of viewing RDDs as local randomized experiment? Again, as I was saying at the beginning, the causal estimate are causal estimates that reflect or apply to a subpopulation of units. And this subpopulation can also be characterized, for example, in terms of the distribution of the covariates, and therefore results from such estimates of causal effects are more easily generalizable, as opposed to, so they, let's say, they could be used and may have also better external validity. And so, again, effects can be more easily generalizable or extrapolated also away from the cutoff point. We can also focus, we are free, let's say, to choose estimates, as for example, was the case in our application, where leprosy is a rather rare event, and therefore relative risk as opposed to an ATE, an average treatment effect, is more appropriate. We don't need to necessarily model the relationship between the running variable and the outcome, and causal effects are not necessarily additive, as instead is oftentimes the case when using the continuity approach. Sorry, and the treatment, because the treatment assignment is random as opposed to being assumed essentially deterministic, we can use also finite population inference, so Bayesian inference, but also inference based on the randomization distribution, which is instead, let's say, impossible with this other approach characterizing RDDs and as non-probabilistic assignment mechanism. This approach can also easily account for discrete running variables without having to rely on on assuming some kind of underlying continuous running variable. And because we have an actual subpopulation of units the causal effect will refer to, we can a lot better visualize covariate balancing, which is something that, for example, is very appealing for doctors or for practitioners, to actually see the population, how the population, the causal effect applies to, looks like. If in fact the units around the cutoff point are in fact comparable, or they look alike in terms of the distribution of the covariates. Other questions here? No. Okay, so I can proceed. So the main problem, and almost the only problem, let's say, in these local randomization approach is the selection, is identifying, so selecting these subpopulation that we have only assumed existing, but we do not know who are the units belonging to these subpopulation, okay? So several methods have been proposed in the literature, mainly based on falsification tests. So essentially, for units for whom that belong to these subpopulation, because the local randomization assumption should hold, we are expecting, for example, the covariates to be equally distributed on either side of the threshold. So essentially, all these tests essentially run, we typically run tests to assess whether for specific subpopulation of units around the cutoff point, the distribution of the covariates are balanced. So we usually start with, let's say, a small bandwidth, test, see whether the covariates are balanced, and possibly increase for essentially efficiency reasons. We try and find the largest subset of units around the cutoff point for whom the randomization assumption is plausible. It's plausible because the distribution of the covariates is expected to be the same if the local randomization assumption holds. This type of falsification tests, and we have, you know, tests, Bayesian test and randomization-based tests have been proposed in the literature, are not easily, let's say, generalized under the local unconfoundedness assumption. So they can only be straightforwardly applied in when assuming local randomization. And again, for when assuming local unconfoundedness, usually some other methods are used to select the subpopulation. For example, penalized matching methods, as in Keel et al. But also as in I think this paper by Keel et al. Has features in common with a recent paper by Ricciardi, Baio, and I don't know who's the third author, Silvia Liverani, right? Which essentially also used covariates and to try and find homogeneous clusters of units around the cutoff point, right? So maybe we can talk more about the relationship with these and other papers next. What is instead, and now I'm coming to our proposal. So the problem, sorry, first maybe the problem of these methods, apart from being, let's say, complicated or becoming not so straightforward under the local unconfoundedness assumption, but essentially they have problems of scaling up. They usually assume a shape, namely they take all the units around the cutoff point in a certain, I don't know, interval of values of the forcing variable. And also, most importantly, and this is also a feature or a flaw also of the of estimators in the continuity approach, they do not account for the uncertainty about the selection of the subpopulation. So, for example, also the the estimators that are used in the continuity-based approach, where a bandwidth is chosen for the semi-parametric estimation of these jump, do not account for the uncertainty on the bandwidth, right? And this is where our proposal comes into play, in that we propose to select US0, viewing this selection as a clustering problem. So essentially, the sample units in any RD study may be partitioned into at least these three subpopulations. So we have units that we would like to identify that belong to US0. And then we have units with a value of the forcing variable above the threshold for whom the local randomization assumption does not hold. So they have some residual dependence of the potential outcomes on the forcing variable, and also units with the value of the forcing variable below the threshold for whom the local randomization assumption does not hold. And we try and include these information on these three subpopulations in a, let's say, clustering methods that amounts to specifying a finite mixture model for the joint distribution of the potential outcomes and the forcing variable. Essentially, this joint distribution can be written as a mixture of these three distributions, where, as you can see, the three distributions are involve mixing these three mixing probabilities that may depend on covariates, and then the specification of the joint distribution of the potential outcomes and the forcing variable, where for units belonging to the subpopulation that we want to identify, namely for whom the local randomization assumption holds, if you can see here, their distribution of their potential outcomes given covariates is free of the forcing variable. And essentially, the idea is that depending on the configuration of both the forcing variable and the covariates, units with values of the forcing variable that are close to each other and also close to the cutoff point may belong to different subpopulations. So not necessarily units that are very close to the cutoff point, not all of them are chosen to belong to US0. And then once this mixture model is specified with, and again, I'm going to now give you some information on the data, but essentially we let the Bayesian inference do the magic, essentially. And within these, by deriving the posterior distributions of the parameters of all these distributions, we can also derive the posterior distribution of any causal estimate, namely contrasts of Y0 and Y1 for these subpopulation, accounting also for the fact that the belonging of these to this subpopulation is uncertain. So the probability of belonging to US0 may be different from 0 and 1 for most or of the units. Okay, so here are some, can you tell me how much time do I have left? Or I'm already out of time?
I mean, normally these talks carry on until around about 3 o'clock, sometimes
okay.
Slightly earlier. I mean, it doesn't have to finish at 3 o'clock. Some people will drift away at 3 o'clock.
Okay, but I'll try to finish within 5 minutes so that we have maybe time for questions or so. So here are some descriptives, let's say, of our data. And obviously all the eligible families have a value of the forcing variable below the threshold 120. The leprosy rate in terms of cases per 1,000 families are the ones you see here. So overall, you would see, let's say, little benefit, or actually being eligible appears to be, let's say, bad for you, right? So this is, of course, not a causal contrast, just because, again, the ones that are eligible are in fact a lot poorer than the ones that who are not eligible. Therefore, all this problem of assessing the effect of eligibility for units around the cutoff point. Those are the background, and so the covariates we also used for and conditioned on when specifying the models that I showed you before. So we have covariates describing the household structure, some characteristics of the household head, and also some living and economic conditions of the family. Here are some details of the model specification that we used, namely, we used conditional probit models for the mixing probabilities, log normal models for the per capita household income, and again, a probit model for probit models with different coefficients and also specification depending on which of the three subpopulations we focus on for the outcome. Okay. And here are some details of the priors. We essentially use weekly informative priors for all of the coefficients. And again, we focus on finite sample estimates, namely, we essentially imputed the missing potential outcomes within the MC algorithms for all of the families, and specifically all the families that at a specific draw or step of the MC algorithm belong to US0. Okay, and by doing that, here is what we got, and maybe I finish with that, and maybe leave the last slide for comments and questions and, let's say, ideas for future research. So essentially what we gathered from these results. So first of all, around 50% of the units that we have in our sample belong to these subpopulation for whom the local randomization assumption is plausible. Of course, with the variability here. And this is the number of units that are included in these subpopulation with, and again, these accounts for this is the uncertainty we account for that is usually not accounted for in other approaches, right? Most of the units within these subpopulation are eligible. So only a little, let's say, or smaller fraction of units with value of the forcing variable above the threshold are in fact included in the in US0. And those are the features, the distributions, let's say, of the forcing variable within the three subpopulations. Okay, so as you can see here, as I told you before, not all, we do not impose a shape on US0. So units that are relatively, let's say, away from the cutoff point may still belong to US0 depending on the configuration of their covariates, right? So it essentially for the likelihoods and that are involved in the posterior distribution, they are more likely to belong to these subpopulation as opposed to the other two. This is the posterior distribution of the relative risk of leprosy that I mentioned earlier. The effect is, let's say, below 1, although the 95% credibility intervals do cover or does cover 1. But in fact, there is some evidence that this relative risk is essentially less than 1. And again, I do not have time to comment much on these results, but it's essentially a causal effect which can be viewed as an average over the distribution of the proportion of units belonging to these subpopulation. And in a way, this kind of idea is has also been used in other observational settings. This is just as a contrast. Those are the results of a similar Bayesian analysis conducted, however, on the subpopulation of units chosen with the usual frequentist, let's say, bandwidth selection, right? So essentially, once the bandwidth is chosen, all the units in the interval around the cutoff point are used for estimating the jump. And again, of course, we do not know which is the right answer, but essentially what we can observe here is that the posterior distribution is shifted to 1. Actually, it's always above 1, and but it's also a lot more precise, right? So it's the width of these of the 95% credible intervals are smaller. So in our view, they are essentially shifted, possibly in a biased way, just because they include a lot more units with value of the forcing variable above the threshold, and also estimate these, let's say, possibly biased causal effect in a much sharper way. So it's, and again, they do not account for the uncertainty in the bandwidth selection. So here are just some concluding remarks summarizing some of the things that I have already told you. So I maybe stop here